So good evening everyone. Let us get started. So last day we discussed about the relative values of inductance and inductances of the two windings for the DC motor, that is field winding and armature winding, and after that we started discussing, or we started understanding about electromotive force, as we know as EMF. So what is EMF? We'll start here from here. So as per Faraday's law, if there is some coil, the coil has some flux linkage, the coil is in some magnetic field, in some environment where magnetic field is there, so that means some flux will be linking that coil, and if that flux changes with time, then that will cause some voltage to get induced across the two terminals of the coil. So that is Faraday's law of electromagnetic induction. So after that we discussed that the flux linkage of the coil could be due to, say, coil 1, it could be due to its own flux, due to its own current, and it could be due to some other conductors, some other coils current. Say there are two coils, say coil 1 and coil 2. The flux linking the coil 1 could be due to its own current, or it could be due to its some other coil's current which is linking the first coil. So this is the flux linkage due to its own coil, and this is the mutual flux linkage due to coil 2. Here I am discussing only a case for two coils. Now we discussed that induced EMF then will be d dt of psi 11 plus psi 12, and psi 11 we know that it is the self flux linkage multiplied its own current, and mutual flux linkage 12 is basically the mutual flux linkage multiplied by the other windings current. So the inductance may change with position, with some movement, and current can change if it is a time varying current. So this can be written as ddt of L11 I1 plus ddt of L12 I2. Now because both can change with time, so we have to take uh, partial differentiation. First we will consider the inductance to be constant. We will have di1 dt, plus then we will hold the current constant. We will take the partial differentiation of self inductance with, say, it is a circular body which is rotating at some angular velocity, so its position is or indicated by theta. So the rate of change of inductance with position, with change in position, that multiplied by d theta dt, or this can be written as omega. So d theta dt is nothing but the angular velocity omega. So this is due to the first term, and similarly second term gives, first considering the mutual inductance to be constant, di2 dt, plus even again partial differentiation of mutual inductance with position, and omega multiplied by omega. So these are the two terms, and we just rearranged it. So this first term does not depend on speed, but the second term actually depends on speed, right? So this is known as transformer EMF, and this is known as motional EMF. After that uh, we quickly went through or saw
Sir,
some
I have a
examples.
question here.
Okay, okay.
Sir, we are thinking L11 will change with respect to angular position. Then
Yes,
in the first part of the equation, which we mentioned as transformer EMF,
yes.
then could you please comment on the L11 value which has to be considered there?
Yeah, I'll discuss when I come to that corresponding case.
Okay, sir. Thank you.
Okay. So the first case we'll consider uh, current variation in the same winding, that is we are concerned with winding 1 and the current of that winding itself is changing. So this is the first case. So this is a stator, we have some winding dot cross, again dot and cross, and the winding is injected with some sinusoidal current as indicated here, I1 varying with time, I1 varying with time. So how is this? This is basically we have some winding here, and similarly we have some winding here. So you have two terminals. This is the winding we are talking about. So there is some current injected into that I1, and that I1 basically varies with time. That is a sinusoidally varying current. So if we have this case, then uh, you can see that if you visualize the flux lines, how that change. So basically if the current changes, then the flux linkage of that coil also changes, because um, uh, uh, the mmf basically changes, and so flux changes, so flux linkage also changes. So we can see that the current as well as flux linkage are in phase, and current is also sinusoidally varying with time, and flux linkage is also sinusoidally varying with time. Now if we remember Faraday's law, so induced EMF of the coil E1 will be d psi 1 dt. So if we have sine, so differentiation of sine is cos. So we would have, if we plot the induced EMF of the coil, then this red one is nothing but the E1 induced EMF, which is leading the flux linkage by 90 degree. So this is the induced EMF. Now if we want to represent this physical winding as a electrical equivalent circuit, then you can understand that we have to model the um, losses. Because of I square R, there will be some copper loss happening in the coil, because the coil has some resistance, so some I square R losses will be there. So that will be represented by a resistance. And the inductance, if we have the inductance, then the voltage that gets induced due to the time varying current, that is basically modeled by the inductance. So this is the self inductance of the coil L11, and so this is the resistance of the coil R1. So this is the electrical equivalent circuit model of this winding, which I have indicated. So the physical winding is like that. If we try to model the um, model the physical winding with electrical equivalent circuit, then it can be represented by this thing. So if there is some current flow, so current is changing, so the inductance will have some voltage across it. So that is nothing but L11 di1 dt. So this is how we can this is what induced EMF due to current variation in the same winding is. So this is self flux linkage varying with time, and this can be modeled simply with RL circuit. Any question here? Okay, then let me go to the next one. That is, here we have two coils.
Sir, in the previous case which we have discussed, there is no variation of inductance, right?
There is, you can answer. Is there any variation of inductance?
No, no, I guess.
Yeah. So rotor is cylindrical, so the air
Yes,
gap in between remains the same even if it
yes, sir.
rotates. So there is no variation of inductance.
Yes, sir.
Now the second case we have two coils. So this is say first coil, and we have second coil. So these are the two coils we are having, and both are wound on a magnetic core. Now say if we pass some current, say this is coil 1 and this is coil 2. If we pass certain current, say I1, into that into the first winding and keep the other winding open, and if we try to see what happens. So this is the I1 current, which is, again we are injecting some sinusoidal current, and if we try to look what is happening in the core, so we know that some flux lines will get will be established in the magnetic core. So this is how the flux lines will be, and with current it will be varying. So following the previous case, the flux linkage of the same winding, that is coil 1, will also be in phase with the current which is causing it. So psi 1 is varying like this, as you can see. Now because the psi 1, all the flux lines, what we have just seen, all of them go through the magnetic core, and the other coil that is also wound on the same magnetic core. That means for this specific case, all the flux lines which are generated by the first winding, if we neglect leakage, probably some say some lines like this, which are which are which are here, which are linking only part of the first winding only. If we neglect that, that is quite negligible in this case, because we do not see any lines uh, when we saw the animation. That is quite low. It is not that such lines are not there, but that is quite low. So you can see that almost all the flux lines, they are linking the second coil also. So if flux linkage of the first coil is psi 1, then the flux will be psi 1 by N1, if N1 is the number of turns. That same flux, say total flux is say phi 1, phi 1, part of phi 1 may be leakage, phi L1, and part of that may be mutual, phi M, phi M1. So this phi M1, so this part is almost quite negligible, so we are neglecting this part as of now. So almost all the flux is going and linking the second coil. So the flux linkage of the second coil psi 2 is nothing but number of turns of that second coil N2 multiplied by the flux that is coming there, and that is approximately equal to N2 into phi 1 only, because leakage flux is quite negligible here. So psi 2, so and again phi 1 is nothing but psi 1 by n, so N2 psi 1 by n. So you can see that psi 2, that is nothing but number of the turns ratio multiplied by the flux linkage of the first coil. So this is just a scalar, so it does not give any phase lag or lead to the second flux linkage. So you can see that both the flux linkages are in phase, and they are only scaled by the number of turns. That is because I have put a different number of turns here. So you can see here peak flux linkage is close to 5 milliweber turns, but here it is close to just little higher than 2 milliweber turns. So now if we try to represent this system as a with equivalent circuit model, then how can we do that? So the first coil, so let us try to see what all things are there. So you have the terminals of the first coil. So the first coil will have some resistance, winding resistance, which will have to put, and then it will have some small leakage inductance, which is which I indicate here. So apart from that, there is a this is a coupled coil. So there are two coils which are coupled to each other magnetically. So this is a coupled coil, and this is the second coil, and the second coil is open in this case. So if there is some current through this, if the mutual inductance between the two coupled coils is M, then if I1 is changing, I1 is varying with time, then there will be some induced EMF here on the second coil, and that will be M di1 dt. So this is the induced EMF of the second coil. So psi 2, because psi 2 is like this, so the induced EMF of the second coil will be sinusoidal like this, similar to the previous case. So this is the induced EMF E2, and for this case it is open, so we need not, there is no leakage inductance. So if because it on its own it does not have any current, so we need not indicate the resistance of the winding and leakage inductance. But suppose we close it with some load, say resistive load, then we have to, where there will be some leakage flux that will be that will be linking the coil 2 only, that may not link the first coil. So there will be some leakage inductance of the second coil, and there will be some winding resistance, and here will be the terminals of the coil which are connected, which are connected to a load, external load. So this becomes the electrical equivalent circuit of this coil, where we are discussing the induced EMF due to current variation in another winding. So this is coil 2, some induced EMF is there because of current variation of a magnetically coupled first coil. So this is the case of a transformer or coupled inductor. This is the case of a transformer as well as coupled inductor. So coupled inductor is nothing but a transformer. So transformer, you try to ensure that most of the flux, 98-99% of the total flux, actually goes and links the other coil. Coupled inductor, you may do as per your requirement, how much flux you want to couple with the other coil, that you can do. You can decide the coupling factor based on your requirement. So that is the second case. Is there any question on this? Okay, so these two constitute the first part, that is the transformer EMF, where we need not include a back EMF or voltage source separately. The inductance, either self or mutual inductance, can be used to model the induced EMF. Now we come to the third case. So third case, the structure is like this, where we have some salient poles on the stator. We have some teeth, some slots, and similar salient poles we have on the rotor also, as you can see here. And we have some winding put here. So this is the winding on this side, and this same thing is coming, and we have the second. So these are the two terminals of the coil. Now you can see, if the coil is injected with, say, constant current I1, which is constant, and the rotor rotates, for this rotor position, for the first case, or probably I will make it rotate, that will be easier. Now the right hand side picture, you can see that the flux, that is, some current is flowing to the coil, and because of that there are some flux lines, and the number of flux lines are quite low, only 4 flux lines you can see here. Now if I make the rotor to rotate, you can see that as the rotor pole comes and aligns with the stator pole, the air gap, so the reluctance of the flux path, that basically comes down drastically, because for this case you have so much path of flux line through air. But if I go to the next path, so that is here you can see that the flux lines, the flux path, the length of the flux lines in certain part has reduced a bit. And if the rotor rotates further, then you can see that in this portion, in this overlapped portion, you have only the small length of air gap. So the inductance of the coil increases significantly, and as I go further, here there is more overlap, so the reluctance reduces further, so the inductance increases, and it reaches the perfectly aligned position where the inductance becomes maximum. Then again, as it starts going, and it again the overlap angle, I mean, if this is the stator pole, if this is the rotor pole, the portion where they are overlapping, this is this angle, whatever angle it subtends at the center, that is what I'm mentioning at it as mentioning as overlap angle. So now as the rotor is moving in the anti-clockwise direction, you can see that the overlap angle starts reducing, and now there is no overlap, so inductance is reduced drastically. And again, as the next pole comes, again the same phenomena happens to the coil inductance, it increases, now it reaches peak, and again it starts declining. So this thing happens uh, continuously. Now you can see that if I mark this as the pole which we are looking at, so this pole has come and aligned and gone here. Now you can see that the pole with which you started is actually here, and the next pole has come here. Next, if again the same thing will follow, and the pole with which we started has actually come here. So rotor has not yet made a full rotation. Again rotor continues, and the pole with which it started reaches here, but 3 times the inductance of the coil has risen, and again it has fallen down. And again in the fourth part, the pole with which we started reached its initial position, that means one rotation is done, one rotation is completed. But in one rotation, how many times the inductance of the coil has increased and decreased? How many times?
4 times.
4 times. So in this case, 4, what can you see, which number is 4 in the rotor? You have 4 number of poles. So for this type of machines, for one mechanical rotation, one full mechanical rotation, the inductance of any one coil has 4 cycles. So 4 times it completes. We will go to the next one, how the inductance, how the flux linkage of the coil changes, and we will see that there are 4 cycles there. So for these machines, unlike your AC machines, you have electrical angle and mechanical angle, there is some difference. Here also inductance is an electrical quantity. So if inductance changes, if there is a cycle of inductance variation, we will call as electrical cycle, and mechanical cycles remain same. If the rotor completes one rotation, that becomes a mechanical cycle. So here we are looking at the current. The current, you can see that it does not change with time, but the flux linkage changes. Initially it is low, then it increases, then it reaches maximum, then again it comes down. 1/4 of rotation, mechanical rotation, has been completed, but one cycle one cycle of the flux linkage is done. This is a periodic quantity, so in that period, whatever one the duration after which it repeats, that we call as one period. So one period is of 10 milliseconds in this case, but rotor has rotated only by 90 degree. Then again in the next 90 degree it again increases, reaches peak, and again comes back. Rotor has rotated by 90 plus 90 180 degree. Then again rotor rotates, reaches peak, and comes back. Rotor has rotated by 270 degree, and again another one, total 360 degree. So in 360 degree of rotor rotation, you can see that in flux linkage there are 4 cycles which have been completed. So the electrical, if we try to define electrical angles, then whatever is the period electrically speaking, this thing we have to, this duration will be 0 to 360 degree electrical. So this aligned will be half of that, 180 degree, and this is how electrical angle will be for this case. Those are little tangential with respect to the topic that we are discussing, but you can see that the flux linkage of the coil changes. Now because the flux linkage of the coil changes, d psi, there is some d psi 1 dt. Now this coil has some inductance. So we have seen that psi 1 is nothing but L11 I1 plus I1 dou L11 dou theta into omega, right? This is the flux, or sorry, this is the induced EMF, d psi 1 dt equal to induced EMF, whatever we have discussed. Or sorry, yes. So the flux linkage was psi 1 only, but once you write the induced EMF, you have two terms, L11 I1 dt plus I1 dou L11 dou theta into omega. Now the first term, the inductance, self inductance itself changes, depends on rotor position. So this is also not a constant term, it depends on L11, that depends on rotor position theta, and this dou L1, anyway this is a function of theta, it has to be. So and this is the induced EMF. If we are injecting any current, then obviously there is going to be some resistive drop also. So if we have the physical winding, we have to, if we want to represent that electrical circuit in terms of electrical circuit, first we have to use the winding resistance, then the inductance of the coil, which is L11, which changes with rotor position, rotor rotation, and after that we have to add a induced EMF, which is again dependent of some induced EMF, say E1, that depends on the current, that depends on the rotor position, that's all, and it also depends on speed. So this is your electrical equivalent circuit for this type of coil. And how this back EMF will be, this back EMF, you can see that when it is rising, inductance, that means inductance is also rising, means dou L dou theta, that is positive. So in this region you have positive back EMF, and in this region you have negative back EMF, again positive back EMF and negative back EMF. So in the rising portion you have positive back EMF, and in the falling portion you have negative back EMF for this coil. So does it, so how to solve this? Suppose you want to solve, you want to so a simple RL circuit. So if a machine, uh, okay, we'll come back to it, at this point of time. Is there any question when we are going to the modeling part?
Sir, you are saying L11 is something, L11 as a function of theta, and even has another L11. Is that okay, sir? What I'm
Yes.
thinking is I am getting two times the voltage induced across the inductor twice from the circuit you have given.
No, 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 no. If see, if you pass some constant current, if I only model with say L, L is only a function of rotor position. Say, and we are injecting
Sir,
I
have you
equal to
got my
I1.
point?
So, come again?
Uh, did you got my point, sir? What I'm thinking is we
Come
are
again.
counting the voltage across the inductor twice. I'm thinking
No, you are not
from the
doing that.
circuit we
Why?
have.
Suppose I suppose let us consider that this is the equivalent circuit, and if I inject I equal to I1, a DC quantity. Suppose you are telling that okay, you have the resistance, you have the inductance, and the inductance is L11 is a function of theta.
Yes,
Okay. Now
yes,
say
sir.
I am injecting some constant current I equal to I1. Will this inductor have any voltage across it?
No.
But in the actual case you have some induced voltage. So that is why you need this term where induced EMF is a function of current, rotor position and speed. So even if you pass a constant current, this part does not have any voltage across it, but this term, this part, the in E, the voltage source which I have put, that has a voltage across it. But if I pass some time varying current, say this I equal to small I1, which is a function of time, then both this will have some current, this will have some voltage which is L11 into di1 dt, and this part will the induced EMF will depend on the instantaneous current, rotor position, and uh, yes, it will depend on that. It
Yes,
will
sir.
depend on
But
how that partial differentiation of inductance changes. Yes.
yes, sir. In the in the expression you have shown E, right? Is
Yes.
that E and E1 are same, or E1 is just a function of second part I1 dou L11 by dou theta into
So this whole
omega?
thing is E.
Okay, okay, okay. If that is the thing, I'm okay, sir. I'm okay.
So this part is E, and this part is
Okay,
E1.
okay, okay. Thank you, sir.
Okay. So this whole part is being, so this is the whole E which is being modeled by one inductor, which is the inductance value changes with rotor position, and one voltage source whose EMF depends on current, rotor position and speed. That is the
Yes,
model.
yes, yes. In that case, our E is equal to L11 di1 by dt plus E1.
Yes. So this thing is E1.
Yes, sir. Okay, okay.
So our E1 is I1 dou L11 dou theta into omega. That is why I have mentioned it E1 as a function of I1, theta and omega.
Okay, sir. Got it. What I thought is E1 is the same as E. I
No, no,
initially thought.
no, that is not the case. Okay. So if this is clear, then let us go to the induced EMF due to mutual inductance variation. So in this case, we have again two. So unlike the previous case, we have two windings. So we have one winding here, one winding similar to the DC field winding, and we have another winding. So say suppose we are injecting some current I1 in the first winding, obviously it will have its other part also. So this is our I1 that is going in like this and coming out like this. So this is the first winding, and the second winding is here we have one, and another we have another winding. So the cross and dot I have put just to indicate the related the convention, the sign convention, but there is no current through the second winding. So the first winding, say it is a constant current similar to the previous case. So the first winding is conducting some current I1, which is constant, equal to 1 ampere as I have shown in this case. So and the rotor is rotating. So even if the rotor rotates, you can see that the flux that will be linking the first coil will be remaining more or less constant. You can see that the blue waveform shows the flux linkage of coil 1 that remains more or less constant. Why that small jitter is there, will come to that. But you can see that as it rotates, it remains more or less the same. So for this position, for this rotor position in the second figure, if you see, all the flux lines come and link. So this is one flux line. It obviously links the first coil, but given the polarity, it links in the opposite direction. So if the second winding has any current of this polarity, then the flux direction will be opposite to the flux direction in this case. That is the only case. But you can
Sir,
see that all,
sorry. Sir,
yeah,
sorry. How you are giving that convention? Could you please mention?
I am not arbitrarily giving.
No, sir. Like why you have you are saying there is no current,
Hmm.
and why you are taking cross and dot on the rotor?
This is a convention. So if this is dot and cross, some current is flowing, then there will be some flux linkage. Flux linkage can be positive or negative, right? So if we leave this open, which
Yes, yes.
flux
I
linkage
got.
shall we tell as positive and which flux linkage we shall tell as negative? For that
Okay, sir.
only.
Okay. Got
If
it.
we
Got
if
it.
we
You
if
are
we Sorry, come again.
you are thinking in such a way that if I suppose the current flowing through that conductor, if it is in this direction, then the flux will be upwards, and
Yes.
that direction is taken as positive. But in our case, the flux is
Yes.
moving from top to bottom, so we have taken it as a
Yes.
negative at the zero
Negative.
instant of time. Okay, okay, got
Correct.
it, sir. Thank
That
you.
is all. That is all. It is about the sign convention. Okay. So you can see that all the flux lines which are flowing from the top are actually linking the blue coil, linking the coil on the rotors. All the flux lines, as you can see. Now if I run it as the rotor rotates, let me stop and show you at multiple positions. Suppose the rotor has rotated up to this. Now you can see that these flux lines are linking. This flux line is uh, linking the coil, but you have some flux line. This is, say, another flux line which comes and does not enclose the conductor at all, right? You can see that the other flux line what which I drew earlier actually goes on like this, and it encloses this conductor, but the red flux line does not enclose any conductor. That means for this rotor position, the red flux line does not link the blue conductor. But earlier, all the flux lines were linking the blue conductor. That means as the rotor starts rotating, then the flux linking the second coil starts reducing, and as the conductors become vertical, Yes, as the conductors become vertical, little bit left. Yes, as the conductors become vertical, if I indicate 1 flux lines on each side, so this is the innermost flux line, or the, yeah, or the outermost flux line in terms of the yoke, and you on this side you have the flux line like this, the black flux line. You can see that neither the green flux line nor the black flux line encloses the blue conductor. That means at this rotor position, the flux linking the blue conductor is 0. So earlier at this position, it was all the flux lines were linking the blue conductor, but in the opposite direction. That is why it had negative flux linkage and negative peak flux linkage. With rotor rotation up to some point, probably like this, still all the flux lines are linking the blue conductor, so it is reasonably constant here. Then flux linking the blue conductor starts reducing, proportional to the angle by which it rotates. So here it reduces to 0. This is the instant where I have stopped now. This is the position where the flux linking the second coil is actually 0. Now as it rotates further, you can see that some flux lines are linking the second coil, and at this rotor position it again reaches maximum. So it reaches maximum. So actually it reached maximum little ago, probably here. So it reached maximum flux linkage here, and after that it remains reasonably constant for some period, and it same thing repeats as it rotates another time. So this is how the flux linking the second coil changes with rotor rotation. Now the second coil does not have any current flowing through that, and the first coil current is also constant. So what is changing here? The mutual inductance between the mutual flux linkage between the second coil and the first coil, psi 2, that is changing there. And psi 2, what is psi 2? Psi 2 is nothing but L 21 into I1. I1 is constant, so that means this L21, the mutual flux linkage between the second coil and the first coil, that is changing because psi 2 is changing and I1 is constant. So if you divide this psi 2 by I1, you will get the how the mutual inductance is varying with rotor rotation or rotor position. So that is why in this case the induced EMF of the second coil d psi 2 dt, I1 remains the same. So you have mutual inductance varying with rotor position, and that multiplied by d theta dt, that is nothing but the speed. So you have this back EMF. So if I try to represent the second coil in this case, the second coil obviously will have some back EMF, some induced EMF, which is a function of the first winding current, the inductance or the rotor position to be specific, and the speed. So this induced EMF, say E2, E2, E2 is a function of first winding current, rotor position, and speed. So this is how you will have to represent the second coil. And again the second coil will have some inductance, its own inductance, and it will have its own some small resistance. So this will be the electrical equivalent circuit of the second coil, and the first coil will have to represent by a resistance and a inductance of the first coil, and this one there will be mutual coupling between the two. So this is how you have to represent. So how will be the induced EMF? So wherever you have rising portion, there you will have positive induced EMF. Wherever you have flat portion, there you will have zero induced EMF, and wherever you have falling portion, there you will again have negative induced EMF. So if I try to draw the induced EMF, thinking this as the zero line, so there will be some positive induced EMF between here to here, some zero induced EMF in these regions, again some negative induced EMF in this region, and again some zero induced EMF in this region. So this is the type of induced EMF that you expect in this type of a scenario. And if you now see this properly, this is nothing but the case of a DC machine. A DC machine, the first winding is the field winding, and the second winding I have only represented one coil of the armature. So if you excite the field winding with some constant current, and if you rotate, suppose it is a generator, you rotate the rotor with some other motor or some engine at a constant speed, and if you measure, if you have access to the coil terminals, if you have access to the coil terminals, normally you don't have, because they come through commutator and brush. So if you had the access to the coil terminals, then you would be able to see induced EMF of this shape. So this is induced EMF due to mutual inductance variation. Is there any question on this?
Sir, how will we get the site to analytically? You have simulation, you can, but is
Come
there
again.
any way site to, sir, flux linkage in the second coil?
Obviously
How
it is
can we
possible.
get?
So if you have the flux density distribution, if you assume that flux density, I have to discuss. Okay, probably. So earlier we have been discussing about the flux density
Yes,
distribution along the ear gap.
integral H dot dl.
H dot dl, like that you can get the B distribution along the ear gap. So B distribution is, B is almost constant under one pole, another pole, and it falls from the positive value to 0 in the other pole. If I have, I don't think I have that in this slide, but I can probably erase this one. So we can have the B distribution. So this is B under one pole, it falls to 0, and again it is B under another in the interpolar region, this is 0, again this is under another pole, and this is how the B, most correctly this is radial component of B as theta varies. This region is nothing but this region, and this region, the second one, is nothing but this region. We have already discussed this quite a few number of times. Now what is going to be the flux linkage of the coil? Now see, at this position the coil terminals are at 0 degree and 180 degree. So the coil terminals are at 0 degree, 180 degree. So what is the flux linkage of the coil? You have to simply integrate whatever you have got from 0 to 180 degree, 0 to pi. If you have this, say this is some B, and you assume that it falls linearly to 0, and again it comes to linearly here, you take some approximation of this shape, then you can integrate this is integration. So this is nothing but the area enclosed. So this is a rectangle, this is a this is a these two are the circles. So you can get the area, and that area indicates what is the flux. So you get the flux at this position. Now as the rotor rotates, say it comes here, say it comes at 90 degree and 270 degree. So for this case you have to take integration from 90 degree to 270 degree. This is the now you have to calculate the area enclosed. Now you can see whatever is the area enclosed on the positive side, same is the area enclosed on the negative side. That is why when the conductors are at 90 degree and 270 degree, it is 0. Now again the rotor rotates by another 90 degree and it comes here. Now you have to take integration from pi to 2 pi, so it is negative. So in this case you get negative whatever. So I mean to say, whatever you got, whatever sign of flux linkage you got when the coil was 0 degree and 180 degree, you get the opposite when the coils are at 180 degree and 0. That means it has rotated by 180 degree. This is how you get it. Does it answer your question?
Yes, sir. Yes.
Okay. So that is why the B distribution, whatever we have taken so long to discuss the B distribution along the air gap, that is important to uh, get all these things analytically. So you can get the induced EMF also. Now I'll just start with this and we'll stop soon in 5 minutes probably. So this is the DC machine case study which we are going to take. So here we have armature slots, 12 number of slots, and some field winding is carrying some current, 1 ampere, number of turns per stator pole, that is 500, that is 500 turns are there here, and again 500 turns are there on the other pole. And there are 50 small 50 conductors. This is just a number, this can be 10, 20, whatever. Say I have taken 50 conductors in each slot, okay, in each armature slot. So this is the case we have taken. So you know, so we will see what happens if, so how do we get the electrical equivalent circuit or the dynamic equivalent circuit of the field winding, armature winding, and the combined DC machine electrical equivalence, dynamic equivalent electrical circuit. Now we know uh, how to represent coils, how to represent winding in electrical equivalence. So we will see what happens, what is happening to the flux linkage of that, and we will derive that. So we will probably do the field winding. So the field winding, if it is excited with some current and the rotor is rotating, say at 1500 rpm, just a number. So this is the rotor rotating, the field, the armature windings are not having any current flowing through them. So you can see, if you look at the flux distribution here on this pole, if you just try to see that, you can see that it remains more or less the same. It changes, the distribution changes little bit with rotor position, but the value, but more or less it remains. The number of flux lines does not change with time. You can look at, you can see that there is some sense of movement of some flux lines on the pole, on the pole body, but it is negligible. There is the meaning is the flux linkage of the first coil, even if the rotor is rotating, that does not change much. So if I plot from simulation, so here this is the field winding. So the field winding is injected with 1 ampere of current, and if I plot the flux linkage of the field winding, you can see that it remains more or less the same. You can see this is actually the scale is not from 0, this is from 3.25 to 3.75. So we have looked at a zoomed in version of the actual plot, and we can see that there are some oscillations on the, so there is some constant DC value, and about that there is some increase and decrease. Now why is there increase and decrease? Because of the number of slots. If you count, this is one rotation, and we have how many slots we have discussed? 1 2 3 4 5 6 7 8 9 10 11 12. We have 12 slots. Now if you count, this is the 0, 1 2 3 4 5 6 7 8 9 10 11 12. So this jitter is directly related to the number of slots that you are having in this case. So if you try to look at carefully at this instant, you can see that there is some case. So you have a slot opening in the rotor just after the stator pole, and again symmetrical picture, same thing is there, and under the pole actually you have 3 slots. So for this case you have the minimum flux linkage for this case, and if the rotor rotates by some angle, some small angle, now you can see that the next slot opening actually is little bit away, next slot opening is little bit away, and under the pole you have 1 2 3 and 4 slots. So as the rotor rotates, keep on rotating, then these two cases appear, so again and again. So for one case you have 3 slots under the pole, and the other 2 slots are at the edge just away from the stator pole, and again this case where there are 4 slots under the pole, and it is the picture is like this. So for this case, the current case rotor position, you have the maximum flux linkage, and for the previous one you have the minimum flux linkage. That is all. So that is all the variation you have. But you can see that because of this variation, obviously there is going to be some induced EMF, because there is going to be some uh, so this inductance of this field winding will be varying little bit with rotor position. So this is the current I constant, and this is the flux linkage of the field winding. So because the current, so L or psi f, that is nothing but LF into IF. IF is constant, so whatever variation in psi f is there, that is due to variation in LF. So strictly speaking, the LF is function of theta, the LF is function of rotor position. So with rotor position there will be a small quantity of induced EMF, but that is negligible compared to, that variation is very negligible compared to um, say the induced EMF that will be there because of varying current, if there is for across the inductance. If DC current is flowing, and again no induced EMF will be there, no transformer induced EMF will be there across the winding. So this winding, this field winding, all the small variation is there. But again, mind you, this is the case for a 12 slot machine. A 12 slot machine, actual cases the slot number may be quite big. So in that case, the small jitter that you are able to see, that will be further negligible. So we will be able to see that the dou LF dou theta, whatever small variation is there, that can be neglected for all practical purposes. So for this field winding, if you want to represent it in terms of electrical equivalent circuit, then if these are the two terminals, then obviously the winding will have some resistance, and it would have some inductance also, that is the self inductance LF, that is reasonably constant. Strictly speaking, that is function of theta, and for that case you will also have another component, that is back EMF, but dou LF dou theta, that is reasonably close to 0, and LF is reasonably constant with rotor position, so this can be considered as a constant number, and this term can be considered to be 0. So this becomes the electrical equivalent circuit of the field winding. So if you apply VF, here is some current, so this becomes the electrical equivalent circuit of the field winding. Is there any question here? Okay, so we'll stop with this. So mathematical or electrical circuit model. So electrical circuit model we have already discussed. We have to have some resistance, we have to have some inductance. So these are the two terminals where we'll have the input, that is Vf, and the current will be If, and there will be some flux linkage corresponding to the current. So the equations go like this: Vf equal to If Rf plus Lf dIf dt. This is the equation. So if you have to solve it, suppose you want to represent it as a system where the input is Vf, you want the output as If and If, say, then how do you want to solve it? You would have the input Vf, you would have to subtract this IFRF, so IFRF has to be subtracted, then you have to divide it by 1 by LF, or multiply it by 1 by LF. Then you would have to take the integration of that. Integration will give If, that will have to be fed back, multiplied with factor of RF, and that goes as IFRF here. So this becomes your If, and another output if you want a simple gain. So gain can be represented instead of square gain. A typical symbol for this is a triangle like this. So if you multiply it by LF, then you get psi f. So this thing becomes your model of the field winding. If you want to mathematically solve it, mathematically simulate it, then this is how to get it for some voltage. So this Vf can be anything. This Vf can be a constant voltage. It could be 0 for certain period, then you give a step input to the voltage, and then you again give a step reduce step to 0, or you reduce it to some other value, or you increase it by a ramp, all those things you could have. But for all these cases, if you give the input whatever you want, this model can give you the output as the current. So if you want to solve it, if you want to model your field winding of your DC motor, you can. This is how you have to do it. Here we stop. Is there any question? Okay, I'll stop the recording.